Perfect. Yeah, thank you.
Okay, there we go. Well, thank you, Robert, for that introduction, and thank you, Michael, for the both of you for the opportunity to speak to you about this important topic. Appreciate the invitation. Just a quick outline of what we'll try to cover today. We have to get into a little bit of the climate change fundamentals because we need to understand how much confidence we should have in projecting future extreme weather. But then I'll try to focus on some of the individual phenomena, and hurricanes are the big one around here, but we'll talk about several of the other types of high impact weather that can be affected by climate change. And hopefully, if I don't get bogged down, we'll have time for some discussion at the end. But in approaching this talk, I was thinking about, well, what would a policymaker, what questions would they have about climate change and extreme weather? And I've read several documents that were designed for policymakers and realized that some of the questions are things like, what's going to happen? When is it going to happen? What will the impacts be at various scales? How could policy improve those outcomes? And details certainly about crafting and implementing the policies. Well, I'm a geoscientist, and as a geoscientist, I care about several of these things as well. But geoscientists tend to be focused on why things will happen and what processes are involved and are we representing them adequately, and really focused on how to optimize projections and quantify and reduce uncertainty. So in terms of information, the United Nations, of course, has played a huge role with the Intergovernmental Panel on Climate Change. The latest assessment report is about to come out next year. But also in North Carolina, Governor Cooper signed Executive Order 80, and one of the things mandated by that was the North Carolina Climate Science Report, which I was a contributor to. And so that was an interesting document because it certainly tied into policy issues. But as a geoscientist, we tend to lean most heavily on the peer-reviewed scientific literature, very technical. So I think that sometimes there's a lack of interaction between policymakers and geoscientists, and I've seen this in various capacities. But reading the documents that Robert provided and the UN Sustainable Goals document, one of the objectives of that was to increase or strengthen the science policy interface. And so hopefully this talk will do a little bit of that. I think if policymakers know the science, then they can address skepticism and more efficiently implement policies. And if scientists understand the policy side, they can provide information that's needed to clarify the scientific uncertainties and how we know what we know. So there's a lot of benefit to those interactions. Just related to that North Carolina Climate Science Report, Dr. Ken Kunkel, who's the lead author on that report, he put together, we had a plain language summary and several media events and presentations. And this slide is sort of modeling an example of a high-level summary slide looking at global surface temperature as a function of time. On the graph here, going back to 1900 and projecting forward to the year 2100. And this says what's going to happen. It says when it's going to happen, and it says how things might change with different policies. And we know that one of the goals of the Paris Agreement is to, keep the temperature change, below 2 Celsius or a goal of 1.5 Celsius. And to do that, we really need to be on this lowest emission scenario. If we don't do quite as well, we'll get the 2 to 4 degrees Fahrenheit of warming. And if we continue on our current path, it'll be more like 5 to 9 degrees of warming. But this is just an example of a summary slide that shows how enacting different types of policy could change the outcomes. Another theme I wanted to touch on here to get going is public trust in science. And on Saturday, I was putting this talk together, and I went to one of our local television stations and grabbed the 7-day forecast off their webpage. And it shows what a lot of them show, which is there's no error bars. There's no information about uncertainty. And we all know that as you get farther ahead in the forecast cycle, the greater the uncertainty. The high today will probably be quite a bit warmer than 82, for example. But the point is, this is a deterministic forecast. You're providing a single number out into the future. There's no indication anywhere here that there's less confidence in that 7-day forecast than there is in the 1-day forecast. And we know from careful studies that forecasts lose skill. These kind of deterministic, single number forecasts lose skill after a week or two, even in the best of circumstances. So then that leads to skepticism. People say, if we can't trust the forecast out 2 weeks, then why should we trust a 100-year climate model projection? And so I think that continued reliance on these type of deterministic weather forecasts has actually hurt the credibility of climate science with the general public. And it's important for people to adopt a probabilistic view of both weather forecasts and also climate projections. The response to the point on the previous slide is that different processes act on different timescales. And this is something I think a lot of people don't fully appreciate. An analogy I like to use is that you can make a pretty accurate prediction of the tides without predicting each individual wave and when and how far up the beach it will go. But the individual waves on the beach are kind of like weather systems in the forecast, but the tide is more like climate change. It's a slower process that's dictated by different physics. And so we can predict it even if you can't get all the individual waves right. Speaking of time scale, I just wanted to go through a little bit of background here. If you have a fast response thermometer and you measure temperature, say over the course of 1 hour, you'll see these small scale fluctuations happening quite quickly. If you look over the course of a day and you look at the temperature, you'll see these fluctuations with a high in the afternoon, a low in the morning. You can look over the course of a year at the monthly means and you'll see that annual cycle. But when you're talking about climate, you really need to think longer time scales. If you look at, say, a 500-year hypothetical slice of temperatures, you'll have some decades where it's colder, maybe some warmer periods, maybe some overlying trends that are even lower and even operating on a slower time scale. And when we're talking about climate and climate change, we really need to be thinking on time scales of decades or longer. And so it's tough when you have extreme weather, which happens on a very short time scale. How do you relate that to these slower, longer time scales? So I'm not going to go through this slide in detail because there's lots of information here, but I wanted to get across the point that there's lots of different mechanisms that cause climate change. And most of them are natural. The continental configuration will cause climate change on timescales of hundreds of millions of years. And right now we're in a situation that's very favorable for a cold climate because we have high latitude land masses that can favor glaciation. We don't always have that. We know that there's astronomical factors like the orbital cycles that give us fluctuations on tens of thousands of years. And we know there's solar climate, everything from the 11 and 22-year sunspot cycles to much slower variations in solar output that can extend out billions of years. Greenhouse gas concentrations can cause climate change on the order of, probably tens to hundreds to thousands of years. And they can be either a forcing or a response to climate change. We have volcanoes, aerosols, land use changes, natural variability in the system, things like El Nino. So all of these things are associated with different timescales and they're all acting all the time. So the question is, why do we often focus on greenhouse gases when there's all these other mechanisms? And the answer there is that, first of all, we know that human activity has significantly influenced the concentration of some greenhouse gases. And we also know that we're changing these gas concentrations very rapidly compared to these other forcing mechanisms. And we also know that when you emit a gas like carbon dioxide, it sticks around. It has a very slow time scale in the ocean atmosphere system. And so if you emit a bunch of CO2 into the atmosphere, you're going to be stuck with it for a while and its effects. And so these are all reasons why we focus on that type of forcing. But it doesn't mean that there's not other mechanisms at work. We're not saying that there's not other mechanisms at work. And it doesn't mean that we're saying that past climate change was all driven by greenhouse gases. In most cases, it wasn't, because we weren't doing what we're doing now. So another question that comes up is people will say, well, you know, these greenhouse gases constitute a minute fraction of the atmosphere. They're almost all the greenhouse gases are much less than 1% of the atmospheric composition. They're measured in parts per million or parts per billion. And water vapor is a little different. We'll talk about that later. But, you know, what do you say when people say, well, what's so special about carbon dioxide and water vapor and methane and other greenhouse gases? Because they make up so little of the atmosphere. And to talk about that just a little bit, again, probably a lot of you know this or have this background, but we'll just go through this quickly anyway. You know, when you have a sunny day, a sunny warm day like today, it doesn't get warmer because the sun is heating the air. The sun shines right through the air with very little absorption below the ozone layer. But what the sun does is it heats the surface, and then the surface in turn heats the atmosphere through outgoing radiation and other transfer mechanisms. But the outgoing radiation emitted by the Earth is lower energy, longer wavelength type radiation that can interact more with atmospheric gases compared to the solar radiation that comes in and the atmosphere is mostly transparent to it. So when you look at the greenhouse gases, they all have they're at least triatomic. They all have at least 3 atoms in their molecules, whereas oxygen and nitrogen and argon have 2 or 1. And the way it works, the way these molecules interact with radiation, and this is an audience participation graph here. We could get each person to do one of these molecular motions. But each type of molecular vibration or rotation or oscillation interacts with infrared radiation. The other gases can't do that. So only gases that have more complex structures can interact with infrared radiation. So even though there's not much of them, they're the ones that matter because they're the ones that can vibrate and oscillate in ways that allow them to absorb infrared radiation. So some basic textbook plots here. If you didn't have an atmosphere at all, the sun would shine down, heat the surface would emit long wave radiation, and you'd have some kind of equilibrium temperature, which for the Earth, with its current amount of reflection, would be about 0 degrees Fahrenheit. So if it weren't for the atmosphere, it would be very cold, probably uninhabitably cold, because then you would have lots of ice and snow, and then that would cause even more radiation to reflect, and it would end up even colder than that. In fact, the temperature of the moon is colder than that, which has no atmosphere. But thankfully, we do have an atmosphere. So the sun shines through it, hits the surface emits radiation, and some of that outgoing long wave radiation is absorbed by greenhouse gases and re-emitted in all directions. And some of that comes back down to the surface. So you end up with more radiation reaching the surface than you would without an atmosphere. And as a result, the average surface temperature is about 60 degrees Fahrenheit warmer than it would be without an atmosphere. And this is, you know, a basic calculation we can do, you know, from really fundamental principles. But we're thankful that we have greenhouse gases because that's what makes the Earth's habitable. But it also should be no surprise to anyone that if you add more greenhouse gases, then you'll get a stronger greenhouse effect and more surface warming. So that's, you know, the flip side of it. And that's really the issue, is that if you look at the so-called Keeling curve, since the late 1950s, they've been measuring carbon dioxide at Mauna Loa Observatory in Hawaii. And this little sawtooth pattern is due to biological action. We're nearing our annual maximum now, but then as the leaves grow and vegetation grows, it'll absorb some carbon, and then that will bottom out going into the fall, and then increase again as those leaves decay. But the sawtooth pattern isn't the main story. The main story is that there's this trend from pre-industrial levels, 280 parts per million. Now we've blown past 400 parts per million. It's now about 420 parts per million. So, never again in our lifetimes, even those of us that are very young, will we see CO2 below 400 parts per million again, unless we can come up with some great carbon sequestration strategy really fast, because it's on the way up and it's not going to go back down anytime soon. The other point that sometimes people say is, well, if you look at the radiation coming from carbon dioxide, it's just not that much. And in a sense, that's true. But when you add carbon dioxide, you get warming. And when you get warming, you get more evaporation and more water vapor. And water vapor is a very strong greenhouse gas. So if you add some CO2 and you get some warming, then you get more water vapor, which enhances the effect. And the net amount of warming you get is actually more than half due to water vapor. So, it's kind of a bogus argument to say, well, the CO2 isn't doing it. Well, there's an additive effect, which is called the water vapor feedback, that amplifies the warming you get for a given amount of greenhouse gas increase. So we can look back historically. This is a graph. So now is on the right side of this graph, and then time goes backward to the left, going back hundreds of thousands of years. And this is taken from an ice core that they drilled at Vostok, Antarctica. And the red line shows the past CO2 concentration, which they can recover in various ways, one of which is by extracting the air from trapped bubbles in the ice at different levels of the ice core. And then the blue line shows a proxy for temperature, which they can infer from isotopes in the ice. And so what you see is that there's a pretty good correlation between carbon dioxide and temperature in the past. But since time is increasing to the right, you see that in a lot of these cases, the temperature actually gets warmer before the CO2 really increases rapidly. And so it's not necessarily true that the CO2 is causing these warm periods where the blue line goes up, but it's probably amplifying that effect due to increased biological activity when it's warmer. Probably these types of fluctuations are caused by orbital changes because it matches the theory there. But now if you look over on the far right, I've circled this area here. Notice that there's this little red spike that goes way up. Well, remember where we are. We're up here where this red dot is. Look at what is going on. So if you go back hundreds of thousands of years, the CO2 hasn't been anything close to 420 parts per million. And look how quickly this is happening. I mean, we're conducting a massive scientific experiment with the atmosphere where suddenly we're up at 420 parts per million. And we're doing it really fast when you look at the time scales that we have historical data for. And so there's going to be very rapid changes in the Earth system because of this, including things like ocean acidification, sea level rise. We don't know exactly what's going to happen, but we would like to find out because we're imparting a huge a huge shock to the system here by ramping up the CO2. So let's see. If there's a question, I'll take someone. Raise your hand if you have a question, and I'm happy to answer it. The last historical graph I'll show. This is from the Hadley Center, which is one of the world-leading global average surface temperature research groups, where they do all sorts of data retrieval to come up with past temperature for the global average surface temperature. And, I've been teaching about climate change, for quite a long time, since the 1980s. And so, you see where we are on this graph. It's not a monotonic increase where every year is warmer than the previous year. There's oscillations, little stair steps on here. There was a time in the early 2000s where people were saying, hey, it hasn't gotten warmer for a decade. See, climate change is a hoax. And then it kept ramping back up. For a while there, the sunspot people were saying, well, it's going to go back down as we get into the next sunspot cycle. It didn't. The people that published those papers have been very quiet recently. No, it's going up, and the only way really to explain it is through greenhouse gas forcing. And we can talk more about how we know that. One of the key tools that we have as climate scientists are these general circulation models, or GCMs. And these are sophisticated numerical models that couple land processes, ocean, atmosphere, ice, and represent the Earth system and its climate with increasing sophistication. And what you can do is you can take these models and start them back in pre-industrial times or in the mid-1800s and see, well, how well can they replicate what has happened between the 1800s and now? And you can run these models including or excluding different types of forcing. And what you find is that if you don't include greenhouse forcing, you can't explain what's happened. There's just no other physics that can do the job. To get the answer reasonably right. Now on this graph, I should point out, so time is going to the right, and this is showing temperature fluctuations. The black line is the observations, and the kind of reddish orange line here is the average of the best GCMs, and you see they can represent pretty well the observations, but you have to account for greenhouse gases, aerosols, which is volcanic eruptions mainly, and the variations in solar output to really get that close to right. But there's pretty good ability of the models to represent what's happened in the past. And it's not perfect, but it's a good way to test the hypothesis that this warming is due to greenhouse forcing. And there's these modeling centers all over the world, different nations and consortia of nations have them. And starting back in the 1990s, and the United Nations was involved in organizing this, but the different modeling groups around the world said, hey, let's get together and compare our models. And they formed what's called the Coupled Model Year Comparison Project, or CMIP. And that has proven to be incredibly valuable because we can then form a consensus from all the different models. Now, the CMIP 5 is the one that most climate scientists have been working with recently, but the CMIP 6, I'll talk more about that in a minute. That's just coming out now, and it has some new information that differs from what we had before. But the point is that these models do a good job of capturing what's happened in the past. And this shows another example. All these different orange lines, the spaghetti-looking lines on this chart, showed all the different modeling centers and all the different model simulations. And when you average them together, what you get is really good. But we know that you need an ensemble of computer model simulations so that you can measure the uncertainty, but also so that you can have a more robust result. And this is used in both weather modeling and climate modeling. And because the atmosphere is chaotic, that's one way to sort of get the signal extracted from the noise, which is the chaotic nature of the atmosphere. So we can use these models, having some confidence in their physics, to project future climates. And to do that, we don't call it a prediction, we call it a projection for several reasons. First of all, the projections are not meant to tell you exactly what we think is going to happen. What they're designed to do is to tell you what would the climate system do if you added a certain amount of greenhouse gas, which is different than saying this is what I think is exactly going to happen. Because there's certain types of forcing, like volcanic eruptions, that aren't in there. They're not supposed to be in there. How could you anticipate there's going to be a large volcanic eruption that will affect the climate in the year 2041 or something? You don't really, you could maybe randomly put them in if you wanted to represent that. But really what we want to know is, if you have a certain greenhouse emission scenario, what will that do to the climate? And that tells us what type of emission strategies we should be adopting to have a certain climate outcome. And these representative concentration pathways, or RCPs, are what were used in the CMIP-5. So all the different modeling centers ran the same kind of experiments. And some of them, if we can go with electric cars and renewable energy, maybe we could achieve the RCP 2.6. And the 2.6 is, how many watts per square meter of heating do we get? A more realistic scenario might be the RCP 8.5, where you get 8.5 additional watts per square meter coming down. And you see that either way, there's a lot of warming in the Arctic and the high latitudes. But you can see that there's very strong warming in degrees Celsius with the RCP 8.5. And you can look at precipitation changes as well. These are graphics taken from the UN IPCC, the 5th assessment report. The 6th assessment report will be coming out next year. That's going to be highly anticipated. Sea level rise, I know that's something that Robert mentioned at the start. When I've looked into this a bit, it's amazingly complicated because it's so localized. And for example, here in North Carolina, the observed rate of sea level rise at Duck is twice what it is at Wilmington. It's very localized and depends on lots of different effects, including local subsidence of land and local effects that are surprisingly influential. But overall, we can project for a given emission scenario how much rise would there be, and that's due to both thermal expansion, some change in salinity, but also how much land ice melts. But we won't talk too much about that today because we want to get to extreme weather and climate. I mentioned the CMIP-6. It's exciting as a climate scientist, but it's also scary because with the CMIP-3 and the CMIP-5, which are the two most recent ones, there wasn't really a huge change in what the climate projections were showing. They were saying, okay, if you increase the carbon dioxide by a certain amount, this is about how much warming you'll get. And that didn't change very much from CMIP-3 to CMIP-5. But now that the CMIP-6 models are coming out with some improved representations of cloud physics and aerosols, what we're seeing is a pretty marked increase in the climate sensitivity. So in other words, they're saying for a given amount of greenhouse gas increase, you get more warming than the previous model experiments were showing. There's a blog here. I should probably paste this into chat so you guys can click on it, but a really nice blog here that really breaks down kind of what's coming out of the CMIP-6 so far. It's not fully available yet, but there's enough of it that's available now that can be used in the next IPCC assessment report. But it's different. It's not showing just a status quo. It's showing increased climate sensitivity. And there's a lot of new experiments. So there's a lot of science that can be done with all the output from that CMIP-6 when it is fully available. But we're supposed to be talking about weather and extreme weather and climate change. And we know that the cutting edge of climate change in terms of its impacts is a lot of times manifest with extreme weather events. And so, this is where it gets really complicated and really interesting. For me as a scientist, I love studying this because there's different physical processes working in different directions. And it really requires careful and varied research methods to figure out which processes are going to dominate. One of the themes is that we know when you have these extreme weather events, a lot of them are driven by the heat released by condensing water vapor when clouds and precipitation form. And we also know that with climate warming, you increase the water vapor content. So right there, in very simple terms, if you add more water vapor, which is the fuel for extreme weather, you should expect amplified hydrologic extremes because of that alone. We also, we can use laboratory experiments and theoretical calculations. We know precisely that, around the range of temperatures where we are, for every degree Celsius of warming we get about a 7% increase in water vapor. There's lots of implications for this. The theory also predicts that we should get reduced frequency of light precipitation and increased frequency of the extremely heavy precipitation events. And we also expect that the precipitation amount in these extreme events would increase more than the average. So there's cause for concern, but how can we study this? The problem is these extreme weather events that are being fueled by condensation of water vapor, they involve small scale processes. And GCMs can't represent those small scale processes because they're too coarse. They have to run for hundreds of years. So they can't have the level of detail to capture those individual small scale weather features. They don't have explicit thunderstorms in them. GCMs don't really have hurricanes. They don't have legitimate hurricanes in them. So how can we study extreme weather? And the answer is by doing something called downscaling. And there's lots of different ways to downscale either GCM output or use other methods to study changes in extreme weather. Just to give you a sense, this is a view looking down on some clouds. And the pixel size here is 100 kilometers, which is sort of typical of what a IPCC class GCM would have. So it's a very boxy looking view of a weather system. If you had the computer power to reduce the grid size, the pixel size down to 50 kilometers, it comes a bit more into focus, but the GCMs aren't really there yet. There are some of the CMIP6 that are getting close to that though in a certain experiment. But you really need to get down to 25 kilometers, which is a typical resolution for a global weather model. That 25 kilometer pixel size, you can start to see a little more of a focus here. But you really need to get down to about 4 kilometers. Then you can start to represent thunderstorms. You start capturing the processes that cause the storm to intensify in the first place. And you realize that this same view is actually Hurricane Florence. The GCM view of Hurricane Florence wasn't very impressive. You wouldn't have known there was a hurricane there. But when you get down to about a 4 kilometer pixel size, then you can really see these kind of intense weather systems come into focus. And it's not really just an issue of sampling. If you have a GCM with 100 kilometer pixel size, it's not going to form a hurricane in the first place because the processes that cause that hurricane are taking place on much smaller scales. So it's just not going to really be able to account for that kind of weather system. So we need to do something else. And there's, like I said, a number of strategies. I'll just quickly touch on one of them here, and that's using high resolution weather models sort of in climate mode. You can take these excellent weather models that can predict the weather in short term very accurately, represent all the processes. Here's a map showing radar and pressure field for a flood that hit Nashville, Tennessee back in 2010. So you can simulate that event and compare it to the observations and know that you've got it reasonably represented. Then you can take the output from a GCM, say the temperature change field, and you can apply that to the model initial and boundary conditions and rerun the simulation for the same weather event, but in a different climate. It could be a pre-industrial climate if you want, or it could be a future projected climate. And you can see, well, how would that same kind of weather system change in a different environment? And we've done this for many different types of weather systems, the same method. We can run it for kind of the whole North Atlantic if we want. We can run it for individual storms like Superstorm Sandy in 2012, or we can run it with idealized weather system like this idealized simulation of a hurricane here. And we can simulate similar weather events in past, present, and future climates at high resolution so we can see how the impacts would change. we did this. Here's just one. I'll just show a couple of examples. We did look at winter precipitation changes. If we kind of look at the end of the century, we get a winter precipitation average that looks like this. The present day looks like this. The difference shows you get drying in the southern North Atlantic basin and in the Mediterranean region, and you get increased precipitation over most of North America and parts of the North Atlantic and Europe. But you can do more when you have these high resolution models. You can also look at how precipitation of different intensity would change. If you look at the change in light and moderate precipitation, you see there's large parts of the North Atlantic and North America and Western Europe that have a decrease in light precipitation. But if you look at the change in heavy precipitation, you see strong increases over the US. And this, by heavy precipitation, we mean 2 inches of rain in 6 hours. So that would be a really heavy rainfall event. We see a large increase in the frequency of those types of events. And that's what the theory says we should predict. Now, if you've watched the news this week, just talking to a friend of mine who was in Lake Charles earlier this week, it's not good. There's extreme flooding. They got more flooding this week than they did from 2 of the hurricanes that hit them last fall. But it's not just that. If you just if you just Google search US flooding, these events, thousands evacuate as 500-year flood destroys 2 dams in Michigan. This is the Nebraska flood 2020 elections. You've got unprecedented flooding in Mississippi. These events are happening with increasing frequency, and that's what we would expect. And you get an impact on the infrastructure, roads and bridges, dams, flooding of low-lying areas, huge economic loss associated with these events. And you can't attribute any individual event to climate change, but if you look at the statistics, here's a graph from our World in Data, shows the kind of the standardized precipitation index, and it's a measure of the amount of land area that experiences a kind of localized extreme precipitation. And this starts in 1910 and goes through 2015. You see that there's this increase, this upturn in the frequency of these types of extreme rainfall events. And that's what we would expect based on theoretical considerations. But it's not just rainfall. You can look at this, there's lots of different ways you can look at weather extremes in the observations. If you look at the percentage of record highs shown in red versus record lows shown in blue, all else equal, you'd expect a record high temperature to be set about as often as a record low temperature. And that was the case in the 1950s. There was a period in the 60s and 70s where we were setting more record lows than record highs. But if you look more recently in the 2000s, for every record low we set 2 record highs. So that's telling us something that we're seeing increasing extremes on the warm side. And even though a lot of the temperature increase we see happens in the daily minimum temperature. There's also been headlines recently and many journal articles in the scientific peer-reviewed literature that weather patterns are becoming more persistent. And here, for the study that we did on this, we defined persistent weather patterns as a strong high or low pressure system that persisted in the same location for at least 5 days. And we studied this because there's indication that there's several journal papers suggested that as you warm the Arctic, you'll see a slowdown of the jet stream and weather patterns. So here's just some of the journal papers that came out about that. But we ran some very careful global model simulations. In our future simulations, there was no Arctic sea ice in the late summer, fall, or early winter. And when we looked at the change in these persistent weather systems, we found that they actually decreased. So there's still a lot of active research, but we did not, we had, I think, a very rigorous test of the hypothesis that we would see increasing persistence of weather systems. But when we ran the simulations, we found little change or even a decrease, depending on whether it was a high or a low pressure system. So not all types of weather extremes will change in the way that, that you expect. But the one that we may have the most interest in, I'm looking at the clock, so I want to go through this fairly quickly, but let's talk a little bit about hurricanes, because we're in North Carolina, the Carolina Hurricanes, that's the name of our hockey team for a reason. We know that there's reasons to suspect that hurricanes would be affected by climate change. Warming temperatures and warmer oceans, like we've said, there's more water vapor, and that's really the fuel for hurricanes. We also, in numerous studies, see an expansion of the tropics, which could mean that we see tropical systems and hurricanes extending farther away from the tropics than we did in the past. There's been studies that show the speed of movement might decrease. And then we also have to look at how the temperature profile changes. And if I have time, I'll talk about how that can work either way. So hurricanes, if you have an initial cluster of thunderstorms and you're over water that's at least 80 degrees, and you're not right on the equator, so you get a little Coriolis deflection, and you don't have too much vertical wind shear that would rip the storm apart, then a tropical cyclone forms, and that could intensify into a hurricane. Where do they get their energy? Well, we have some hot weather coming up this weekend, today too. And say you take a frosty beverage, be it a glass of ice water or a frosty cold beer perhaps, and you take that outside and you notice condensation forming on it. Did you know that for every 20th of an ounce of water vapor that condenses on your cold beverage, that's enough to warm a 12-ounce beverage by 3 degrees? That's about 1/4 of a teaspoon. That's not very much. So that just shows you how much heat is being released, though. And this is why we have things called koozies that basically people sometimes think, well, that insulates my drink and keeps it cold. But no, what it really is doing is it's preventing condensation from warming your drink. And that's how it keeps it cold. Now, if you think about how much heat that is, 1/4 of a teaspoon warming your drink by 3 degrees, and then think about how much rain falls in a heavy rainstorm or in a hurricane, that's a tremendous amount of heat energy. And NASA had a headline recently where they showed that a hurricane over its life cycle releases the energy on average of about 10,000 nuclear bombs. A tremendous amount of heat energy is being released through the condensation of water vapor. So this bluish shape here is a volume of warm, moist air. And this is like the fuel. This is for a simulation of Hurricane Sandy I did. And if we take all this fuel and we add a match, this yellow here shows an area of rotating winds, which is like the flame here. And then we put that into motion. You can see, it kind of jumped there a little bit. That this rotating storm, which was Hurricane and Superstorm Sandy, it's really drawing on all this water vapor as fuel. And then when it moves inland and moves away from that fuel source, then it weakens. But in a warming climate, you're going to increase the amount of fuel and also the northward extent of the fuel. So when we think about hurricanes and climate change, if you look at history, we don't really have that long of a period of reliable observations because we haven't had satellites for that long. So it's hard to really pick out observed trends. But we do, see fluctuations in their frequency. Their frequency hasn't changed much, but we do see an increasing percentage of the really strong storms. But we have to think about changes in the temperature, changes in kind of the thermodynamic efficiency of these storms, and how vertical wind shear might change. These are all things that could change hurricanes. And we know from the GCM projections, it's going to get warmer. So there's going to be more fuel. And we can use that to calculate the maximum potential intensity of hurricanes. And if you take the current climate, you can theoretically calculate, well, what's the strongest hurricane you could get? And the theory matches the observations. We know that with a warm climate, those storms can get stronger. Their kind of upper limit on intensity can increase. The other thing that some research that I did with former student, and Kevin Hill was the one who mainly did this work, If you look at the way the temperature changes in the tropics, so this graph shows cooling on the left, warming on the right, and then as you go up in the atmosphere is the vertical axis. So you get warming near the surface in the tropics, but when you go into the upper levels of the atmosphere, you see even more warming. And so the amount of warming you get up here turns out to be really important to how strong a hurricane can get, because making it warmer there works against the strength of a hurricane. So we did this idealized simulation where we ran a hurricane simulation. And on this graph here, this shows time in the simulation going to the right. And then the lower you are on this graph, the stronger the storm, because it's the pressure of the storm. So if it's a really low pressure, then it's a very strong storm. So this gives us a nice category 5 hurricane. But if we take different GCMs, and some of them have a lot of that upper level warming, some of them don't have as much. For the GCMs that don't have very much upper level warming, we get a really strong increase in the intensity of the storm, way beyond things that we have now. Whereas if you take the GCM that has less upper warming, then you get a different, the one that has the most upper warming, then you get something that's not very different than what we have today. So the amount of upper level warming you get is really critical to how hurricanes will respond. But no matter which scenario you choose, you see stronger future storms in the warmer climate. So to summarize this, there's still a debate about whether the frequency of hurricanes will change. There used to be a consensus that it would decrease. Newer studies saying it might remain steady or even possibly increase. There's also a lot of work going on about the changes and the speed of motion of hurricanes. But there are certain areas where there's an overwhelming consensus. The strongest are going to get stronger. Their precipitation is going to be heavier by a significant amount. And there's going to be increasing coastal impacts, flooding and erosion, partly exacerbated by sea level rise. So even though there's some processes that compensate for this, it's very likely, almost certain, that future hurricanes will become more impactful. And then for an overall summary, we have these increasingly sophisticated GCMs that take into account all the important physics they need to project future climates, except they can't do extreme weather because they're not detailed enough. So we have to use other methods to try to capture those small scale processes and understand how extreme weather will change in the future. And I've just shown a few examples. There's lots of different methods out there that people have used. It's good to use multiple methods so that we can look for common results and have more confidence in them. I've just shown a few examples for the work that we do. But the bottom line is this, the theory and the observations and the models show consistency in certain areas. Increased precipitation extremes, we're seeing it will continue. It doesn't mean that every single weather event is attributable to climate change. I like the analogy of the baseball player on steroids. Any individual home run, they might have hit it anyway, but if they're on steroids, they're going to hit more home runs. And those are the extreme weather events. So, anthropogenic climate change, it's here. What can we do about it? What are we going to do about it? We can adapt, we can mitigate, we can try to limit emissions. The United Nations is a major player in this with the IPCC assessment reports, Paris Agreement. There's a lot of high stakes here. And humans can adapt and mitigate probably, but ecosystems can't. Coral reefs and ocean acidification, there's certain things that are going to be really difficult, and we're going to have to try to limit emissions to really mitigate those types of effects for the ecosystems. So I'd like to thank Robert and Michael and all of you for attending, and acknowledge some former students, funding agencies, and computing resources. And then if I have any time left, I will take any questions, and thank you.
Yeah, thank you, Gary. That was very informative. Yeah, if people have questions, I would suggest that you use the little digital hand. If you open up, let's see, what's the easiest way to do it? If you kind of, click on your own picture, usually you can.
Yeah, Dan, did you have a
Yes,
question?
yes, I do. I have learned so many things. I have just 3 questions that I'll put of many. Is it accurate when somebody talks about global average surface temperature? Somebody says, what's global warming? Is it accurate to say global average surface temperature at all longitudes, in all seasons, all times of day, and over land, ocean, and ice? Is that a fair description?
I mean, the term global warming has fallen out of favor in some circles, being kind of replaced by climate change, because you don't get a uniform warming everywhere. There are some places like southeast of Greenland where you get, very little warming. You can still get cold extremes, so you still have weather. On average, you will have warming at the surface. You'll get cooling in the stratosphere, for example, and some other parts of the atmosphere. So global warming, I think it's a reasonable description. I mean, when people say that, I know what they mean, and I agree that, yeah, you're going to get warming throughout the surface, but there are parts of the atmosphere that won't warm. And so I think that's one of the reasons why that's fallen out of favor a little bit. Does that answer your question?
Okay, so I'm not going to use average surface temperature. Probably don't talk about that.
Well, yeah, it's fine to use average surface temperature. I think
Okay.
that is definitely increasing, and so I think that's fair. People when people look at that number and it looks small, they don't appreciate that. An increase of 1 degree average surface temperature is a huge increase in terms of the climate.
Okay.
And even though it doesn't seem like much compared to the daily diurnal range of temperature, so
Okay.
I think it can be a little misleading, but I think that's fair.
All right. Second, do we know a month when the Intergovernmental Panel on Climate Change report may be coming out in 2021?
Well, I think that the 6th assessment report is due in early 2022, so far as I know. I think the CMIP 6 models are coming out slower than expected, and I don't know. You guys would probably know more about this than I do, because this is really a UN IPCC thing. But my sense is that they've held back on the assessment report to allow more of those CMIP 6 model simulations to be complete. But from what I saw on the web recently, I was just looking at this morning, I think that 6th assessment report will come out in 2022. I think it was originally scheduled for sooner than that.
Okay, final question is, what are isotopes in the Vostok core teaching us?
Okay, yeah, by measuring there's different isotopes of oxygen. You can have O18 or O16, and some of it's heavier and some of it's lighter. And so the lighter, if you have a lot of glacial ice where you've taken the lighter, there's a preference for lighter water to be evaporated, and then that is what gets locked up in ice sheets. So that concentrates the heavier water in the oceans. And so you can look at the ice core and just kind of say, well, what are the average, if you look at the average isotopic composition of water at a certain point in the ice core, that sort of tells you on average globally how much water is locked up in ice versus how much is concentrated, the heavier water is concentrated in the ocean. So you can look at that ratio and say something about how much global ice cover there is. And then from that, you can back out temperature.
Thank you.
You're welcome. Good questions.
I have a question, Gary.
Sure.
First, I want to compliment you on a fantastic talk. I've learned so much from your presentation. I really appreciate that.
Oh, thank you.
The question I have is whether in the climate models there is explicit, where you have a ocean model coupled with an atmosphere model, because it would seem that you need that to do some of these long-term simulations where you could look for these sort of critical states where the atmosphere could be knocked into a metastable state that we couldn't get out of through anthropogenic changes.
Yeah, these are all of the IPCC class GCMs now have coupled ocean atmosphere, and they also have sea ice models and land models. And so they have, a good representation of all these different systems. The ocean models are really critical because when you add carbon dioxide and heat, the ocean models will mix some of that heat down into the deep ocean, and that's a real source of uncertainty in the models. So the coupled they're definitely capable of representing those things, but it's complicated to really get it right. And so, yeah, certainly the ocean models and the deep ocean circulation are something that gets a lot of attention in the climate modeling community. But yes, they are coupled together for sure.
Now, where do you have the computing power to run those models?
Yeah, well, the different different nations, they're putting their best supercomputers towards this effort. So that if you look at the groups, I think there's about 35 different groups, 36 that are now in the 6th CMIP. You've got to have a lot of computing resource, and the fact that the CMIP 6 is running behind because of all these new experiments, I think is a testament to that. So, we can all, if you look at some of the world's fastest research computers, a lot of them are used for climate and weather modeling. In fact, they're almost, generally that's what they are used for. And so, if the computers get faster and faster, we can get, higher resolution and better GCMs. But, for the foreseeable future, we'll always max out whatever computer speed increases come along. But it takes a lot of computing resource to do it. And that's why, only the kind of leading centers around the world can join the IPCC CMIP game.
Right.
Great. I see Al Reardon here. Al probably taught. He could probably have answered. He could have given this talk as well, probably. But I'm sure you taught some of these things too. So hopefully you weren't bored by any of this, Al.
No, thank you. I learned a lot. I got up to about halfway through your talk, but when you started talking about computer simulations, that was new to me. But I had a different question. It looks like we are now in the adaptive mode of reaction to climate change because of roads washing out and people's homes being flooded. The economics are going to drive our decisions because we're way behind in the US on policy. And so I wondered what your reflection is that, not being an economist or something, maybe someone else could talk about it. Go ahead.
Yeah, I mean, I think that really gets to the policy side of the question, which, is not my wheelhouse as much. But clearly, we are changing more to a adaptive type mindset here, because it's going to be really tough. To meet the goals of the Paris Climate Agreement is going to be really, really tough. I mean, we're if you look at the amount of carbon we've already added, so the best strategy is probably to try to do both. Try to do, to adapt, to mitigate, and to limit emissions, to do all of those things as quickly as we can. But yeah, we have a neat project with the North Carolina DOT to help them manage transportation infrastructure, because after what happened with Floyd in 1999, but then more recently Matthew and Florence, and a lot of these storms put major highway systems underwater, and they know that they need to have better stormwater management, because you can't have a city like Wilmington isolated from the outside world like that. And so we really are to the point now where people are saying, look, how can we deal with this? How can we build more resilient infrastructure and get ahead of the curve on these things? Because if we just, try to solve it through reduced emissions, it's too late for that. Well, I see it's 1:07, so I'll keep answering questions as long as you guys have.
Could I just say hello, Bob Larrick? I'm relatively new to the Carolinas, but I'm an old UN supporter and climate change worker. And the politics which you touched upon. Thank you for you representing a science and sanity mental health group also that talks about mapping and focus. I thought you brought those issues up, and the issue, do we need more focus on energy and what we're doing to ourselves politically. I worked on it at the UN, which we got a World Spirituality Summit to work on these things. But the idea of from North Carolina, the Bible Belt or in the Bible Belt, the idea of there's a book by Dowd, Thank God for Evolution, and I would add the determining evolutionary force that created our natural systems and had us, life and us, and don't we need to engage our universal creator and each other more constructively with better energy, more constructive energy for a different type of focus rather than values and politics or supremacy while we're going underwater and the need for momentum, which I thought you brought up in the mapping techniques. And why shouldn't Charlotte and Raleigh and the Carolinas be a leader and models? We have a good World Affairs Council of America in Charlotte. You have a lot of, in Raleigh, there are a lot of good UN and tech people. We have a good health system. And Wilmington, I just heard yesterday, was increasingly important as a deep water port and a business center. And don't we need healthier economies, people, and ecosystems? Why shouldn't Charlotte, why shouldn't the Carolinas be a leader?
Yeah,
How does that sound?
it's a, I hear what you're saying, and I agree. You almost need to, take politics and religion out of the equation if you can, to really try to make it a nonpartisan issue, or to make it a bipartisan issue ideally. But it seems like these days it's really tough to make anything bipartisan. It's unbelievably difficult to do that. So yeah, if it's driven by economic realities like Al was mentioning, and if it's driven by those, then that way you can put it in terms that everyone will agree with, or at least the people that disagree with the science can still see the economic value, then that's maybe going to be a more convincing argument. And there's been a lot of studies of climate change skepticism. Dan Cahan at Yale University has some great papers about this. And what they show is that very well-educated people are actually the most effective climate skeptics, because they're better at finding evidence that supports their viewpoint. So it's not a matter of education. It's a matter of getting people together, trying to make people realize that these types of measures are good for everybody, and it shouldn't be a partisan issue. And then maybe we can make some forward progress. And that's our best hope. But I agree, it can start locally. And if we can, exert some local leadership with clean energy and better transportation infrastructure, then that really is setting an example. And so I'm hopeful that that will happen going forward.
All
So
right.
Thanks for that comment.
Yeah. I do think we're getting to the end of our time, and I want to thank Dr. Lackmann for an excellent set of remarks. And thank you all for coming. I hope you've enjoyed the event, and we will put out news about future events soon.
Well, thank you for having me. Sorry if I went a little long. I know some people had to go at one, but hopefully there's no harm in dropping off then. I enjoyed meeting you guys and learning more about your group, and hopefully we can interact down the line. So yeah. Thanks for being here and for your interest and questions.
All right, thanks.
Oh, I see there's a bunch of chat